As a predictive tool, there are a number of ways that Nash equilibrium can fall short, some of which we've already seen, and some of which we'll cover later. But one common objection is that it can be insufficiently precise, allowing too wide a range of predicted behavior. And in response, various refinements have been developed that try to narrow the set of equilibria so that we can make more focused predictions. So, in this video, I want to introduce two new solution concepts that are both refinements of Nash equilibrium. The first of these new equilibrium concepts comes from the idea that maybe Nash is assuming too much about our opponents, and we don't want to require that they play a perfectly optimal mixed strategy. One way this could manifest is if there's a small chance that they screw up and pick an arbitrary action, which we model as a tremble. Think of pressing a button to select your action, but with a slightly shaky hand such that there's a chance of accidentally pressing the wrong one. We're still assuming that players are rational and are trying to play the best strategy, so we'll look for a profile of best responses, but we want that profile to be robust against possible trembles. And this leads us to our definition of a trembling hand perfect equilibrium. Either a pure or mixed strategy profile can be a trembling hand perfect equilibrium, but we require that every player's strategy be a best response not just to the exact opponent strategies, but also to a sequence of nearby profiles with slight trembles. This sequence needs to consist of fully mixed profiles, where every action has non-zero probability, because in our trembling hand intuition, there's some probability of any button getting pressed, but the sequence needs to converge to the actual strategies the players are trying to use in our equilibrium profile, meaning that profile is a best response to itself, in addition to being a best response against the trembles. So, what sorts of predictions does trembling hand perfect equilibrium make? Well, for starters, it's possible to prove that trembling hand refines Nash, meaning any trembling hand perfect equilibrium is also a Nash equilibrium. But next, if we think about a game with a fully mixed Nash equilibrium, like this rock, paper, scissors variant, the fully mixed Nash equilibrium trivially satisfies our definition of trembling hand perfect equilibrium, because the sequence of profiles can just be the same profile repeated over and over again. And since that sequence is all the same profile, it obviously converges. And since that profile was a Nash equilibrium, it's a best response to itself, and therefore a best response to everything in the sequence. So the much more interesting case is a game like this one, where there are multiple Nash equilibria that are not all fully mixed. Here I've underlined all of the best responses, and we can see that the profiles AA and BB are both pure strategy Nash equilibria. And since neither of those profiles is fully mixed, we can ask for each one whether there's a sequence of fully mixed profiles converging to it where the pure profile is a best response to every fully mixed profile in that sequence. So let's start with AA and think about what it would look like to have a sequence of fully mixed profiles converging to it. Well, a fully mixed profile has to put non-zero probability on every action for every player, so both players' strategies need to put some probability on B and C. We want those probabilities on B and C to converge to zero in our sequence, because we want the sequence to arrive at everyone playing A. But for each of those profiles, player 2 will have some probability epsilon that they play B, and some probability delta that they play C, and epsilon and delta have to both be non-zero for the profile to be fully mixed. And if we think about player 1's utilities in response to any fully mixed profile sigma, where we have probability epsilon on B, delta on C, and 1 minus epsilon minus delta on A, then action A has expected utility 0 because its payoff is the same in all outcomes. But action B has expected utility 0 times the probability that player 2 chooses A, plus 1 times the probability they choose B, plus 2 times the probability they choose C. And those probabilities are epsilon and delta. So B's expected utility is epsilon plus 2 delta, and for any fully mixed strategies that might be in our sequence, epsilon and delta have to be positive, meaning this payoff is larger than the expected utility of A. And so we conclude that player 1's part in this profile is not a best response for any fully mixed profiles that might converge to A. And so we conclude that AA is not a trembling hand perfect equilibrium. On the other hand, for BB, we can try to come up with a sequence of fully mixed profiles where B is a best response and it converges to our Nash equilibrium. Here I'm proposing a sequence of profiles where both players will use strategy sigma I in the ith term of the sequence, and that strategy puts most of the probability on B, except for an epsilon probability on each of A and C, and we'll have epsilon be 1 over 2 to the I, so that the probability on A and C is converging to 0, and our sequence is converging to the profile BB. So we've defined a sequence of profiles that converges to our potential equilibrium, and now we want to verify that each player playing the equilibrium strategy is a best response not just to the equilibrium profile, but also to all of the profiles in our tremble sequence. If player 1 plays A in response to player 2 using the ith strategy in the sequence, then player 1's expected utility will be 0. And likewise, if player 2 chooses A against anything in the sequence, their expected utility will be 0. But if player 1 chooses B, now we need to think about player 2's probabilities. There's an epsilon chance that they'll choose A, landing us in this outcome, an epsilon chance that they'll choose C, landing us in this outcome, and a 1 minus 2 epsilon chance that they'll choose B, landing us in this outcome. And so player 1's expected utility is epsilon times 0 plus epsilon times 2 plus 1 minus 2 epsilon times 1, which comes out to an expected utility of 1. Note that player 2's payoffs for B are also 0, 1, 2, and so we'll get the same calculation when player 2 uses B against player 1's ith mixed strategy. And if player 2 uses C against player 1's mixed strategies, the expected utility will always be 0. But for player 1, the expected utility of C is 0 times epsilon plus 0 times 1 minus 2 epsilon plus 2 times epsilon. And so now we can ask whether playing the profile is a best response to every mixed strategy in the sequence. And for player 2, that's obviously the case. But for player 1, it depends on epsilon. The expected utility of B is 1, while the expected utility of C is 2 epsilon. So we need it to be the case that epsilon is less than a half. And that's true for almost every profile in the sequence, but we should check when I equals 1. In that case, epsilon will be a half, meaning that C will give a utility of 1, and B is still just barely a best response because player 1 is indifferent. So we've now argued that we have a sequence of fully mixed profiles that converge to the profile BB, and for all players, if they play their part in the profile BB, that is a best response not only to this profile, but also to all of the fully mixed profiles in the sequence. And so we've shown that BB is a trembling hand perfect equilibrium. And so there are certain cases where the trembling hand refinement lets us narrow the set of Nash equilibria in the game. The second type of Nash refinement I want to introduce has a very different sort of background motivation. Whereas trembling hand very clearly originates from reasoning about how the Nash equilibrium concept can be improved, the idea of evolutionary stability comes from applying payoff matrices to a very different context, reasoning about equilibria there, and then translating those ideas back to game theory. And as a result, this solution concept is somewhat restricted, applying only to two-player symmetric games. But in that setting, it does provide an interesting refinement of Nash. So, what's the motivation here, and what the heck do we mean when we talk about mutant invaders? Well, as the name suggests, the origin is evolutionary biology, and the idea is that the payoff matrix is modeling interactions between individuals in a population, where actions correspond to different species or different traits, and the payoffs indicate survival or fitness. So in this model, each individual has a fixed action. They are either a hawk or a dove. But they will interact with randomly selected members of the overall population. And so, if the population has different fractions of the various species, the probability that you will interact with them is given by their proportion within the population. So if the population has 60% hawks and 40% doves, that's like playing against a 60-40 mixed strategy. Meaning that, in this example, if a hawk interacts with a random member of the population, there's a 60% chance it's another hawk and a 40% chance it's a dove. So the hawk's expected payoff is 0.6 times minus 1 plus 0.4 times 4 for a utility of 1. And interacting with the same population, a dove would get an expected payoff of 0.8. So, because the hawk's payoff is 1 and the dove's is 0.8, the hawk has higher fitness, and over time we would expect the fraction of hawks in the population to increase. So with the population evolving over time, the goal of this model is to predict what population proportions will be stable in the long run. And the criterion for stability is that if some small fraction of the population randomly mutates to a fixed action, that fraction won't be able to outcompete the general population. We can check that criterion by setting the mutant fraction to some small epsilon and comparing the expected payoff for the mutants against the expected payoff for the population. For this hawk-dove example, we know that the population won't be stable unless hawk and dove have equal payoffs, and so we can start from the Nash equilibrium that makes the players indifferent between hawk and dove, and the symmetric mixed strategy Nash equilibrium of this game is 2/3, 1/3, under which both actions give an expected utility of 2/3. But if we now consider the possibility of an epsilon fraction mutating to always play H, we can compare the mutants' payoff to the populations. Since most of the population, a 1 minus epsilon fraction, is still distributed according to these probabilities, a random individual from the population will get an expected utility of 2/3 when playing against them. But if a random individual from the population plays against one of the new mutants, which happens with probability epsilon, there's a 2/3 chance that individual will be a hawk and get a payoff of -1, and a 1/3 chance that individual will be a dove and get a payoff of 0. Comparing this to the payoff for one of the mutant hawks, a 1 minus epsilon fraction of the time, they'll play one of the standard individuals from the population. And we know the expected payoff to a hawk for playing against this population distribution is 2/3. But then, an epsilon fraction of the time, they'll play against another mutant, in which case we'll have hawk against hawk, and they'll get a payoff of -1. So these first terms are equal because we had a Nash equilibrium. The payoff to playing hawk has to be the same as the payoff in expectation of the mixed strategy. But the refinement here is that we are also checking what happens if the new mutant plays against itself in this rare epsilon circumstance. And in this case, the mutant gets a lower payoff than an average member of the population, and so a mutation to hawk is not able to invade and take over the population. But to fully verify evolutionary stability, we need to check that no possible mutation could invade, and so we also have to investigate what happens if an epsilon fraction mutates to D. In this case, a random individual from the population will most of the time play another, and with probability epsilon they'll play the new mutant doves. And so that random individual from the population has a 2/3 chance of being a hawk and a 1/3 chance of being a dove. So 2/3 of the time they'll get 4, and 1/3 of the time they'll get 2. Whereas for one of the new dove mutants, in the epsilon chance that it plays against another mutant, it will always get a payoff of 2. So once again, the average payoff to a random individual from the population is better than that of the new mutant, and so a mutation that introduces more doves would also not destabilize the population, and we've confirmed that 2/3, 1/3 is an evolutionarily stable strategy. And this solution concept is very much inspired by variations on the hawk-dove game, but we can apply it to any two-player symmetric game. So let's look at this variant of rock, paper, scissors, where ties get a utility of 0.3. This game's symmetric Nash equilibrium is 1/3, 1/3, 1/3, and it gives an expected utility to both players of 0.1, because if I play rock, or any other action, I will win 1/3 of the time and lose 1/3 of the time, canceling each other out, and then 1/3 of the time I will get a payoff of 0.3 for an average of 0.1. So, to see if this symmetric mixed strategy Nash equilibrium is an evolutionarily stable strategy, we should check whether a small fraction of the population mutating to any of the actions is able to invade and push out the current population. Once again, we'll have a 1 minus epsilon chance of a random individual from the population playing another, in which case we know they'll get expected utility 0.1. And then with probability epsilon, our random individual from the population will meet the new mutant playing rock, and against rock, our random individual has a 1/3 chance of winning, a 1/3 chance of losing, and a 1/3 chance of our 0.3 that's better than a tie. And so their expected utility is again 0.1. Considering the utility of the mutant who always plays rock, when they meet a random individual from the population, there's a 1/3 chance of each possibility for an expected payoff of 0.1. And then in the rare case that they meet another mutant, well now, with both mutants playing rock, they'll get an expected payoff of 0.3. And this means that if a random mutation to rock were to enter our 1/3, 1/3, 1/3 population, it would do equally well against the rest of the population. But when those mutants meet each other, they would do even better. And so on average, they would outcompete and increase their fraction in the population, destabilizing our equilibrium. And so, without even having to check the other possible mutations, we now know that this is not an evolutionarily stable strategy. And so once again, our solution concept is a refinement of Nash, which rules out some Nash equilibria as not being robust against mutant invaders, but many Nash equilibria will be evolutionarily stable. So, what have we learned about these Nash refinements overall? Well, there are some cases where they can help us make more precise predictions, and it's interesting that they can arise both from game-theoretic considerations and from a completely separate evolutionary biology model, but in the end, they didn't change our predictions all that dramatically. In the case of trembling hand perfection, there are often much easier ways of ruling out a bad equilibrium than checking for this sort of converging sequence of fully mixed profiles. And with evolutionary stability, we can only apply the criterion to the small subset of games that have two symmetric players. So often, our conclusion will be that the refinements aren't worth the extra trouble, and we should just stick with the Nash equilibria we know and love.